If I told you that a low VRAM personal computer can now generate cinematic-level extreme action scenes, completely free, would you believe it? Today, we're not talking theory. We're directly testing some of the most advanced video models available to see what they can actually achieve in a real low VRAM environment. Hello, welcome to Smart Vision. On this channel, I keep sharing the latest AI tutorials and practical tools. All workflows, materials, and resources from this video are on my Patreon and are available to download after you register. For supporters, I provide extra professional tools and deeper guides. If you like this content, consider subscribing and supporting the channel. Now let's get started. As of February 2026, paid video generation models have entered a new phase. Models such as Sora 2, Veo 3, and the upcoming Seedance 2 are approaching professional, director-level standards in cinematography, motion coherence, physical consistency, and narrative control. However, their pricing is equally professional. Subscription costs, generation limits, and cloud dependence keep the barrier to entry high. This leads to a key question: can open-source models running locally in a low VRAM environment, without cloud reliance or token consumption, achieve 70% to 80% of commercial-grade quality? This episode will put the two best local video tools currently available to the test. Before we begin, let's clarify the test setup. This is not running on a server or professional workstation. All tests are conducted on a consumer-grade Windows PC. The operating system is Windows. System memory is 64 GB of RAM, and the GPU has 16 GB of VRAM. This is a relatively high-end consumer configuration, but it is still consumer hardware rather than enterprise equipment. There is one additional constraint for this episode. Although the GPU has 16 GB of VRAM, every test will use settings that can operate within a 12 GB VRAM limit. That means I will not use configurations that require the full 16 GB. All workflows will remain inside a 12 GB ceiling. This ensures that the results can be reproduced on mid to high-tier consumer GPUs. The goal is not to demonstrate hardware advantages. The goal is to verify what local video generation models can truly achieve under more mainstream and reproducible VRAM conditions. In this episode, we'll test two advanced local video generation models, the quantized version of LTX 2 and WAN 2.2. I've covered both models in detail in previous episodes. If you're not familiar with installation or basic operation, you can refer back to those tutorials. Here, we'll focus strictly on their core capabilities. First, the quantized LTX 2. It supports both text-to-video and image-to-video generation. A key advantage is that it can generate synchronized audio alongside the video, making it a more complete audio-visual solution. Next, WAN 2.2. It also supports text-to-video and image-to-video generation, but it does not provide native audio output. If you need background music or ambient sound, that must be handled separately. In terms of overall functionality, LTX 2 is more comprehensive, while WAN 2.2 is more specialized and focused purely on video generation. From a hardware perspective, both models have similar VRAM and system memory requirements. However, LTX 2 uses a larger text encoder, which results in slightly higher memory usage during the loading phase. One additional point: if inference VRAM demand exceeds the available GPU memory, the system can allocate shared memory from system RAM. This will reduce performance, but under low VRAM constraints, it remains a practical compromise. That is why limiting this test to a 12 GB VRAM configuration is still entirely feasible. Let's talk methodology. If you want truly cinematic, high-dynamic action scenes, prompt design cannot stop at simply describing events. You need to construct a control structure. There are 5 core dimensions: temporal structure, physical logic, biomechanics, emotional drive, and the camera system. Together, they form a complete control chain. First, temporal structure. High dynamic video most commonly fails due to broken time continuity. Instead of writing one continuous block of action, divide a 3-5-second sequence into clearly defined time segments. Each second should introduce a state change. Momentum must carry forward from one moment to the next. Every action should follow a clear, causal relationship. If the timeline is vague, the model will either jump unpredictably or lose motion continuity. Second, physical logic. Avoid abstract adjectives like intense or dramatic. Instead, describe the momentum chain in concrete terms. Explain how force is generated, how it is transmitted through the body, and how it decays or transfers. For example, acceleration creates inertia. Inertia shifts the center of gravity. That shift produces imbalance. The body then compensates and restores stability. This forms a closed physical loop. The clearer the causal relationships, the more stable and believable the motion trajectory will be. Third, biomechanics. Actions must respect anatomical structure. Specify center of gravity shifts, muscle engagement, joint constraints, especially secondary motion. After the primary subject moves, hair, fabric, and handheld objects respond with delay. This inertial delay is critical for realism. Without it, the image feels composited. Fourth, emotional drive. Emotion is not decoration. It determines breathing rhythm, eye tension, body stiffness, reaction speed. When motion is driven by emotion, micro-expressions and body tension become natural. Otherwise, the character appears to execute commands mechanically. Fifth, camera system. The camera must be designed. Specify relative motion direction, tracking behavior, handheld shake, focal length changes. Ensure depth of field, background flow, and motion blur match physical speed. The videos above were all generated using these structured prompts and LTX2. The results are quite good, very natural with no major issues, proving that this prompt framework works. Writing this structure manually every time is inefficient and unsustainable, so I automated the process. Using Ollama locally with Qwen 3 VL, I built a system prompt specifically designed to generate professional video prompts. It doesn't generate video outputs, it generates structured, director-level prompt frameworks. You provide a simple scene description, and the system automatically expands it into temporal segmentation, physical causality chains, biomechanical constraints, emotional drive logic, camera control parameters, and visual fidelity specifications. In other words, the structural design process becomes automated, while everything runs entirely on a local machine. Now let me demonstrate. We input an image and a single sentence, click Run, and within seconds it produces a fully structured, logically coherent cinematic prompt. What if you still get OOM? The simplest solution. Lower the generation resolution. After rendering, upscale using Flash VSR. I've prepared this upscaling module. Usage is straightforward. Download the model. Configure Sage Attention. Select the video. Click Start. Alright, we've completed some basic tests. Now we move on to 4 extreme stress tests. First test, complex physical interaction. A man punches through a giant balloon filled with colored powder and water. We are not testing the explosion effect. We are testing whether, at the moment of impact, liquid, particles, rubber fragments, and the human body coexist physically. We check whether the clothing becomes wet, whether powder adheres to the fabric, and whether the remnants obey spatial conservation. If any element disappears or breaks physical continuity, the system fails. Let's look at the results. The prompt generated by Qwen 3 VL is completely fine. It is very detailed. This is the result from LTX2. The motion itself is correct and follows the prompt closely. However, the powder and water do not actually attach to the clothing. Instead, they appear pre-printed onto the fabric. So it is slightly cheating. Now let's look at WAN 2.2. After punching the balloon, the man seems to realize the balloon is extremely hard and his hand hurts. The balloon even looks like it is made of jelly. That is interesting. Second test, biomechanical occlusion. A ballet dancer spins rapidly inside a laser grid. Her hands repeatedly pass through multiple layers of chiffon while grabbing and pulling. We test whether the legs remain structurally independent under self-occlusion, whether the hands truly deform the fabric, and whether the background geometry stays stable during high-speed rotation. If limbs merge, penetrate unnaturally, or lasers flicker, the spatial and skeletal systems are unstable. Let's check the results. The generated prompt is again very detailed. This is LTX2's output. The motion is generally acceptable, but the dancer seems to have learned teleportation. The pose resets instantly. In combat, that would be very powerful. Now WAN 2.2. The movement looks more human, but it cannot maintain a single continuous shot. The camera operator probably deserves a raise. Third test, semantic metamorphosis. A melting ice tiger roars as it dissolves into flowing water. The water gathers and transforms into real kittens that scatter outward. We test entity continuity, whether cross-category material transformation feels natural, whether melting follows gravity, and whether the transformation has a clear kinetic source. If objects appear from nothing or momentum breaks, the semantic chain fails. Let's see the results. The prompt itself is fine. Here is LTX2's result. The motion works, but it does not seem to understand the relationship between a tiger and a cat. It appears confused about the transformation. Now WAN 2.2. It does not fully understand how ice melts. That part would require more guidance. However, it clearly understands what a cat looks like. Apparently, cats are its true masters. Cute, but controversial. Fourth test, extreme spatial scale. The camera starts from a tiny scratch on an astronaut's visor. It pulls back continuously, passing a space station and Earth until reaching galactic scale. We test long-range spatial memory, continuity of nested detail, and whether an ultra-long zoom-out causes frame jumps or tearing. If the background shakes or spatial relationships collapse, the camera system fails. Let's review the results. The generated prompt is again very detailed. Here is LTX2's output. The camera movement is smooth and natural, although it makes me slightly dizzy. Overall, no major issues. Now, WAN 2.2. There appears to be some visual ghosting in the eyes. I am not sure how to describe it. But yes, great. To summarize, what do you think of the results? This prompt framework does improve video generation to a certain extent. It performs well in standard fast motion scenarios.
10.
However, in more complex extreme scenes, it struggles. That limitation comes from the models themselves. Personally, I find that LTX2 performs more strongly under this structured prompt framework, likely because it uses a more capable prompt understanding model. That concludes this episode. I'm Smart Vision. All resources are available on my Patreon for download. Please like and subscribe. Your support is the biggest motivation for me to continue creating.